Introducing Neglectons, the overlooked particles set to revolutionize quantum computing. In a groundbreaking study, mathematicians have discovered a way to enhance quantum computing by utilizing previously disregarded particles. This finding could potentially overcome the fragility issues that have plagued the development of stable quantum computers. Quantum computers harness the power of quantum bits, or qubits, which can represent both 0 and 1 simultaneously. Similar to the famous Schrödinger's cat thought experiment. However, qubits are extremely delicate, and their quantum states can be easily disrupted by interactions with the environment, making it challenging to build reliable quantum computers. The new research, published in Nature Communications, reveals that when paired with mathematical elements once considered irrelevant, a type of quasi-particle called an Ising anyon could help solve this fragility problem. The revived components have been dubbed Neglectons. Ising anyons exist only in two-dimensional systems and are central to topological quantum computing. In this approach, information is stored not in the particles themselves, but in how they loop or braid around one another. This braiding process can encode and process information in ways that are much more resistant to environmental noise. However, there has been a significant limitation. The only problem with Ising anyons is that they are not universal, said Lauda, a professor of physics and mathematics at the University of Southern California. It's like having a keyboard with only half the keys. This is where the overlooked math comes into play. The team revisited a class of theories called non-semisimple topological quantum field theory, which is used to study symmetry in mathematical objects. In this theory, each particle has a quantum dimension, a number that reflects its weight or influence in the system. Particles with a quantum dimension of 0 are usually discarded. The key idea of these new non-semisimple versions is that you keep those particles which originally had 0 weight, Lauda explained, and you come up with a new way of measuring the weight. The neglected pieces, reinterpreted as particles, filled in the missing capabilities of Ising anyons. The team demonstrated that by adding just one neglecton to the system, the particle becomes capable of universal computation through braiding alone. To understand why anyons are crucial, it helps to examine their peculiar behavior in 2 dimensions. In 3 dimensions, particles like bosons and fermions can loop around each other, and those loops can be undone. In 2 dimensions, however, there's no over or under, meaning that when anyons move around one another, the paths cannot be untangled, leading to fundamentally new physics. The key with Ising anyons is their ability to create superpositions. Because these operations depend on the overall shape of the braiding path rather than precise locations, they are naturally shielded from many kinds of noise. While this finding doesn't mean we'll have topological quantum computers tomorrow, it suggests that instead of inventing entirely new materials or exotic particles, researchers may just need to look at familiar systems through a new mathematical lens.